Hi everyone. Today in this video we will discuss about the calculation of dissociation factor, how it can be calculated and what is the use of this dissociation factor, which is well known as Hoff's factor. Dissociation factor is associated with the strong and weak electrolytes. So what are the strong electrolytes and weak electrolytes? According to the Arrhenius theory, a compound is called a strong electrolyte when it is dissociated in the water and conducts the electricity. On the other hand, weak electrolytes will have less degree of dissociation. And we can also have few of the other compounds which are called as non-electrolytes, which are not at all dissociated, thereby they will not conduct the electricity. Since dissociation is associated with the either strong and weak electrolytes, we will see about these two types of electrolytes. Suppose we have a beaker filled with the water. Within this beaker, if we are going to dissolve HCl, then what happens? Because HCl is a strong electrolyte, within the solution the H plus ions can be observed as well as Cl minus ions are going to be observed, which are dissociated and dissolved. So this is the effect of the solvent, what we call the solvation effect, which dissociate the HCl into H plus and Cl minus. Now let us take another beaker with water. And in this, if we are going to dissolve the acetic acid, when we are going to dissolve the acetic acid, what happens? Since acetic acid is a weak electrolyte, it cannot completely dissociate, but it achieves an equilibrium and it can be converted to H plus as well as the acetate ions. So within the solution, we can observe the H plus ions as well as the acetate ions. Along with these ions, we can also observe the undissociated acetic acid. In this way, strong and weak electrolytes can be identified based on their degree of dissociation. The degree of dissociation can be indicated by the letter alpha. If the alpha value is from 30 to 100%, that means it is above 30%, they can be called as strong electrolytes. Particularly strong electrolytes will have an alpha value nearer to the 100. And when compound is having a degree of dissociation less than 30%, then it can be called as weak electrolyte. So in this way, strong electrolytes will have high degree of dissociation, and particularly in case of HCl, it acts as a very strong electrolyte and it can be dissociated at a high degree when it is dissolved in the water. But still the degree of dissociation of HCl may not be equal to 100%, and we can observe some of the undissociated HCl present in the solution. So this is because of the concentration of the electrolyte and the limitations in the solvation. So what is the effect of the solvent on the dissociation of the electrolytes? For example, if you take the HCl, when it is dissolved in the water, HCl molecule can be separated within the solvent molecules. So some of the protons are going to be separated as well as chloride ions are going to be separated. But at a high concentration of the electrolyte, we can also observe some undissociated HCl because of the limitations of the solvents. But as the solution is going to be diluted, we can increase the dissociation because the solvent molecules can easily separate the electrostatic interactions between the H plus and Cl minus ions. Thereby they can achieve complete dissociation. So dissociation increases as the dilution increases. But at the practical considerations, we may not achieve 100% dissociation even for a strong electrolyte. So what is the dissociation factor? Just we have seen HCl is going to be dissolved in the water so that it is converted to H plus and Cl minus ions. Now dissociation factor can be calculated by counting the number of species before and after dissociation. So before dissociation, we can observe only HCl molecules, but after dissociation, we can observe the H plus ions, Cl minus ions as well as HCl molecules. So here we have to see the each and every type of ion, whether it is a cation, anion or a non-ionic substance. So before dissociation only HCl, but after dissociation H plus, Cl minus as well as HCl, all these are present in the solution. Now by using this, we can determine the dissociation factor. Now the dissociation factor I is defined as the number of the species after dissociation by the number of species before dissociation. So it is a simple ratio of the total number of species after dissociation to the total number of species before dissociation. So now let us see how it can be calculated. So now if you take the case of HCl when dissolved in the water, at time t is equal to 0, that means before the dissociation, suppose 1 mole of the HCl is present. Before the dissociation and dissolution, there is no H plus and Cl minus ions in the beaker. So whatever the concentration of H plus is 0 and Cl minus is 0. But at time t, that means after the dissolution, how many number of HCl molecules are there in the solution? Suppose if the HCl is not completely dissociated and it is undergoing the dissociation, which is indicated by the letter alpha, then whatever the remaining moles of the HCl present is the 1 minus alpha. So alpha is the degree of dissociation here. Then when alpha moles of the HCl is going to be dissociated, they will form the alpha moles of H plus ions and alpha moles of Cl minus ions. So this is after dissociation. Now here the dissociation factor I is equal to the number of species after dissociation by the number of species before dissociation. So we can write 1 minus alpha plus alpha plus alpha. So this is after dissociation. 1 minus alpha corresponding to HCl, H plus is alpha as well as Cl minus is alpha, divided by whatever the number of species before the dissociation, that is only 1 mole of HCl. So if we solve this, we will get the I is equal to 1 plus alpha. So here I dissociation factor is equal to 1 plus alpha, where alpha is the degree of dissociation. But this equation is suitable for the electrolytes having the molecular formula like the HCl. That means which is giving 1 cation and 1 anion. So in order to understand this, let us calculate the degree of dissociation of a few of the electrolytes, and we will see how they are variable along with the molecular formula of the electrolyte. Let us take working example 1. Calculate the dissociation factor of sodium chloride if it undergoes 80% dissociation. So here 80% dissociation is given. That means what is the alpha value? So it is 80 by 100, that is nothing but 0.8. So this 0.8 is the degree of dissociation or alpha value. Now let us calculate the dissociation factor for the given example. So sodium chloride is going to be dissolved in the water so that it is going to be converted to Na plus as well as Cl minus ions. So at time t is equal to 0, 1 mole of sodium chloride is present, but 0 moles of Na plus and 0 moles of Cl minus are present. So after the dissociation, how many moles of sodium chloride is available? We have already seen in the data 0.8 is the degree of dissociation. So 1 minus alpha, that means 1 minus 0.8, which gives the 0.2. So 0.2 moles of the sodium chloride is present. So 0.2 is nothing but 1 minus alpha. Similarly, how many Na plus ions are going to produce? Because the degree of dissociation is 0.8, so 0.8 moles of Na plus as well as 0.8 moles of Cl minus are going to be produced. So here the dissociation factor I is equal to the number of species after dissociation by the number of species before dissociation. So 0.2 plus 0.8 plus 0.8 whole by 1. So which gives the 1.8 as the answer. So for sodium chloride at 80% dissociation factor I is equal to 1.8. Now let us take another example, working example 2. Calculate the dissociation factor of zinc chloride if it undergoes 60% dissociation. So again here 60% indicates 60 by 100, which is equal to 0.6. So 0.6 is the degree of dissociation or the value of the alpha. Now let us calculate the dissociation factor. Zinc chloride, which is represented by ZnCl2, when it is dissolved in the water, it is converted to Zn2 plus 2Cl minus. So before dissociation at time t is equal to 0, suppose 1 mole of zinc chloride is present and 0 moles of Zn2 plus as well as 0 moles of chloride ions are present. But after dissociation at time t is equal to t, how many zinc chloride molecules are present? Because the degree of dissociation is given as 0.6, so 1 minus 0.6, that gives the 0.4. So 0.6 moles of zinc chloride is going to be dissociated and 0.4 moles of the zinc chloride remains undissociated. Now how many Zn2 plus ions are going to produce? Since the degree of dissociation is 0.6, so the number of moles of Zn2 plus is 0.6. Then what is the number of moles of Cl minus? So the total number of moles of Cl minus formed are 2 into 0.6, because within this equation you can observe 2 into Cl minus. So for 1 mole of zinc chloride, 2 moles of chloride ions are produced. So for 0.6 moles, we can observe 2 into 0.6 moles of chloride ions are going to be produced. Now what is the dissociation factor I? Now I is equal to 0.4 plus 0.6 plus 2 into 0.6 becomes 1.2 divided by 1. So which is nothing but 2.2. And here you can observe that the formula 1 plus alpha is not valid. Now this electrolyte on dissociation gives 1 cation but 2 anions. So according to the number of ions produced, the formula will be changed. Now what is the simple formula we can use in order to calculate the dissociation factor for any type of electrolytes? So here we can use one of the formula I is equal to 1 plus alpha into V minus 1. So where I is the dissociation factor, or which is also called as von Hoff's factor, and alpha is the degree of dissociation, and finally V is the number of ions produced in dissociation. So it is not the total number of ions, it is the number of ions produced in the dissociation. For example, if sodium chloride is dissociated, it gives the 1 cation and 1 anion, so the V value will be 2. That is the V, the number of ions produced in dissociation. Now by using this simple formula, let us calculate the dissociation factor for various types of electrolytes. Let us take the sodium chloride, the previous example, which is undergoing the 80% dissociation. We got the value as 1.8, and let us check whether we are getting the same result or not by using this simple formula. So now I is equal to 1 plus alpha is given as 0.8 into V. The V is the number of ions produced in dissociations. When the sodium chloride is dissociated, it gives the 1 cation and 1 anion. So total number of ions are 2. So here V is equal to 2. So 2 minus 1. Now this is equal to 1 plus 0.8, which is nothing but 1.8. So we got the same value when we calculate by using the equation. Similarly, if you take the zinc chloride, suppose zinc chloride is undergoing 60% dissociation, then what is the I value? So I is equal to 1 plus 0.6 into, whenever zinc chloride is going to be dissociated, it gives the 1 Zn2 plus ion and 2 chloride ions. So here total number of ions are produced are the 3. So V value is equal to 3. So 1 plus 0.6 into 3 minus 1. So which is nothing but 1 plus 1.2, which gives the 2.2. So again we got the same value for the zinc chloride. So by using this formula, we can calculate easily for any type of electrolyte if we know the degree of dissociation. Let us take the acetic acid. Acetic acid is a weak electrolyte, and let us see what is the dissociation factor for this acetic acid. Suppose acetic acid is undergoing 1% dissociation. Because it's a very weak electrolyte, it undergoes very less dissociation. At 1% dissociation, what is the dissociation factor? So dissociation factor I is equal to 1 plus, because 1% means it is 0.01 into, when acetic acid is dissociated, it gives the 1 proton and 1 acetate ion. So total number of ions are 2. So 2 minus 1. So by solving this, it is 1 plus 0.01, which is nothing but 1.01. So the I value for acetic acid is the 1.01 at 1% dissociation. Let us take another example, calcium chloride. Suppose it is undergoing the 80% dissociation. Then what is I value? So I is equal to 1 plus 0.8, because the degree of dissociation is 80%. So it is 0.8 into, when the calcium chloride is dissolved, it gives the 3 ions, 1 calcium ion and 2 chloride ions. So 3 minus 1. So again it gives 1 plus 1.6, which is nothing but 2.6. So that is a dissociation factor for the calcium chloride. Now what is the significance of I value, the dissociation factor? Dissociation factor is also called as von Hoff's factor. This is very important whenever the electrolytes are involved in the solution. So one of the important role of the I is the calculation of the sodium chloride equivalent for the drugs. So what is the sodium chloride equivalent? We know that sodium chloride is one of the substances which can be used to adjust the tonicity of the parenteral preparations. So in the preparation of parenterals, the adjustment of tonicity is one of the important requirement. But already the solution is having some drug, and drug may produce some of the tonicity. So which is compared with the sodium chloride. So this is called sodium chloride equivalent. So sodium chloride equivalent indicates what is the amount of the sodium chloride that is equivalent to the 1 gram of the drug which are producing the same isotonicity in the solution. So this sodium chloride equivalent method can be used for adjustment of tonicity, for which we should know the I value. So by knowing the I value, we can calculate the sodium chloride equivalent for many types of electrolytes by comparing with the sodium chloride. And once we know the sodium chloride equivalent value, then we can calculate how much of the sodium chloride is required to adjust the tonicity of the parental preparations. So in this way, in the calculations of the adjustment of tonicity, the Hoff factor I plays a key role. Similarly, another role of the I is in the colligative properties of the electrolytes. What are the colligative properties? These are the properties of the solutions which depend on the total number of species present in the solution. So these properties are independent of the nature of the ions, but they only depend on the total number of species. For example, we have seen that when our sodium chloride is dissociated by 80%, within the solution we can observe the sodium ions, chloride ions, as well as the undissociated sodium chloride. All these can affect few of the properties of the solutions, which are called as colligative properties. So colligative properties depends on the collection of the species within the solution, which may be either ionic or non-ionic. But when we are coming to the electrolytes, electrolytes can dissociate so that they can produce a more number of species within the solution, so they can increase the colligative properties. So here again we can use the I value, the Hoff factor, where in every colligative property we can include the term I, so that we can make a correction for the colligative properties. Apart from this dissociation factor can also be used in the measurement of conductance of the electrolytes at the different types of dilutions. So that's about the calculation of dissociation factor and its applications. If you like this video, please subscribe to our channel and share this video with your friends. Post your comments in the comment box. Thank you for watching this video.